Hello, everyone. Welcome to our presentation, Students' T-Distribution on measuring the inter-rater reliability when the observations are scarce. This is a joint work between Serge, me, and Goran. It's between Logos Global Translation and Localization and the University of Manchester, UK. And our work is accepted to NLP 2023. Recent advances in natural language processing to be held in Varna, Bulgaria, between September 2nd to 8th. Firstly, let's see the motivation of our work. In NLP field, we always rely on human judgment as the golden quality evaluation method. There are ongoing debates on how to better evaluate inter-rater reliability IRR levels for certain evaluation tasks, such as translation quality evaluation, TQE, especially when the data samples, or we call it observations, are very scarce. And in reality, practitioners need to be able to assess the reliability of human MT evaluation based on 1, 2, or minimum 3 human linguist judgments. The structure of our work is that we firstly introduce the little-known method to establish the confidence interval for the measurement value when only one data evaluation point is available. This leads to our example with 2 human-generated observational scores, for which we describe students' t-distribution. To measure the IRR score using only these 2 data points and calculate the confidence interval of the evaluation. Then quantitative analysis of how the evaluation confidence can be greatly improved by introducing more observations, even if only one extra observation is obtained. We encourage practitioners and researchers to report their inter-rater reliability scores and confidence intervals in all evaluations, such that to make the NLP evaluation more meaningful, transparent, and trustworthy. The background of our work: human evaluations have been subject to criticisms and debates about their reliability, particularly when carried out without the strictly defined procedures. We list some reference by Graham et al. 2017, Han and Gladkov 2022, and Han 2022. Despite the inclusion of factors such as quality control and clear guidance, human evaluation results can still vary greatly among different individuals due to subjective judgments that is influenced by factors such as background, personalities, cultures, and so on. Naturally, confidence intervals of human evaluation become the key point to the validity of such work. Let's see our earlier work that is related about measuring uncertainty, where we propose Monte Carlo sampling simulations, or MCSS, to measure confidence intervals of human evaluation, and how many segments can make a statistical difference. Our findings of this paper that we present in REC 2022 shows that minimum 200 segments is needed to make a statistical difference for translation quality evaluation. Let's firstly see the single judgment situation, ARF interval. Abbott and Rosenblatt in 1962 proved the possibility of measuring confidence intervals on a single data point from a mathematical point of view. Later work from Varna et al. 1989 further elaborated A and R's formula with a more narrowed interval generation. So we name it ARF interval by taking the initial letters of their name. This method may appear statistically counterintuitive, but even more worth mentioning here, because as production decisions are very often based on a single quality measurement. It is notable that you can estimate the confidence interval of such measurement. The setup is a requirement that for this method that it presents of supplemental information. This additional data is often derived from an experimentally based prior knowledge or theoretically based rule that were external to be the measurement as arises from the project context. For the translation industry, it is known past performance of a vendor. The width of the confidence interval reflects the uncertainty of the experiments. That is, the wider it is, the less knowledge is available. In a relatively narrow confidence interval, such as in a controlled situations, like the normal distribution, here, y, mu, and sigma are the variables of the varied mean value and the standard derivation. The parameter z represents the standardized variate. For the situation with one observation, let mu with hats be the independent and fixed value that is known before and outside the measurements, and y be the experimental measurement value. Fermino et al. In 1989 gives the following calculation intervals of ARF. This ARF interval contains the probability of mu that is larger than or equal to 1 minus alpha. And alpha meets the following equation with k. This table shows the value matching of k and alpha for both normal distribution and the unknown ones by Fermi in 1989. Let's see one example using ARF interval for translation quality evaluation. Assuming that a translation vendor has been evaluated earlier on certain lines of projects and average result was a score of 96.3. That is the mu hat score. The next translation quality measurement produced by another vendor is a lower rating of 85.2, the Y score. How reliable is this measurement by itself purely from the statistics point of view? And what does it tell us? If we assume the quality measurements are distributed normally, it is logical to take the average value of the previous history evaluations as a predicted value for future outcomes. If we construct the 75% confidence interval for the true quality rating, we need to use k equals 1.8 from the construction by table 1. And the corresponding alpha value is 0.25. Using the ARF interval formula, it will give 90.75 plus minus 19.98. The ARF interval for the true value of quality rating is 70.77 to 100. That means with 70% of confidence interval, is almost half of the measure value of itself. That is, the maximum deviation of 19.98 is 22% of the measurement result, that is 90.75. Although the mathematical precision of the single quality measurement is limited to this level, it can be beneficial to know this limit. For an 80% confidence interval, that is when alpha equals 0.2 for the true quality rating, the corresponding p-value from table 1 is 2.31, and the above formula gives the following ARF value, that is 90.75 plus minus 25.64. In other words, the interval for the true value of quality rating is between 65 and 100. From this, we can see that with 80% confidence interval, the maximum deviation of 25.64 is 25% of the measurement result. From these two study cases, the middle of the confidence interval lies halfway between an earlier average result and the recent lower measurement. We can therefore formulate a good practical rule of thumb. If the single measurement deviates from the average, the true value is likely halfway between the average and the new measurement. Knowledge of this would help not to overreact to unusually low single scores newly generated. The findings we received. ARF interval is very wide, and the worst thing is that it cannot be improved by the choice of alpha. In the table 1 we saw, 0.5 is the narrowest option of choice for intervals. However, this value is considered not high enough to make a significant impact. To the right side of the table 1, the smaller value of alpha is, the wider the result intervals will be. Therefore, choosing alpha value between 0.2 and 0.25 is probably the compromise to make. Evaluations consisting of only one single measurement are not recommended, as there will be a higher chance of bias, as illustrated by our translation evaluation example. How about observations with larger than 1? When a single translation quality measurement is not satisfactory for one of the parties, second quality measurement can be made to validate the first measurement. The settings where the sample size is less than 30 and the standard deviation of the entire population is unknown, students' t-distribution can be used to evaluate a standard deviation based only on the number of measurements between 1 and 30, such as 2 or 3. When the sample size, also known as observations, is very small in comparison to the entire population, in 1908, students designed the student t-distribution to measure the mean errors and the confidence intervals of estimation that was published in Biometrica. So who is students? Actually, his name is William Seeley Gossett. He was working in Guinness store at that time, and from the reference in 2019 by Stephen T. Ziliak, the Guinness Board of Directors allowed its scientists to publish research on condition that they do not mention 1, beer, 2, Guinness, 3, their real name. So William used a student as a pseudonym to publish his result. So when there is only 1 degree of freedom, the critical values for student t-distribution is shown in figure 1, including the confidence level, 1 tail, and two-tail scores. The full list of critical values with more degrees of freedom is shown in this figure 2 for further study. The notation of students' t distribution is defined as below if we use t as a random variable. df is the degree of freedom and n is the number of observations. For example, if we have a sample size n equals 2, we calculate the df equals 2 minus 1 equals 1, and write the distribution as t to t1. For the situation when the standard deviation is unknown, the error bound for the sample mean is defined as below, where t alpha divided 2 is the critical value of t-score, with the area to the right equal to half alpha in figure 2, and s is the standard deviation of the observations. And the overlap x is the mean value of n samples. Then the resulting confidence interval is calculated using the following span: overlap x minus e to overlap x plus e. Let's see another example using student t distribution. Assume we have used the multidimensional quality metric MQM and professional translators for a translation evaluation project. And we got two numbers of overall quality score. QS1 equals 76.85 and QS2 equals 81.99 on a scale from 0 to 100. This is the actually real example from industrial project of translation quality evaluation called WHEEL. We can immediately see that, firstly, QS2, that is 81.91, is 6.7% greater than QS1. And oppositely, QS1 is 6.3% less than QS2. Therefore, QS2 agrees 93.3% with QS1, and QS1 agrees 93.7% with QS2. This is almost 95% agreement, so it looks good for most cases. However, if the pass/fail threshold is 80, with the difference may be crucial for the translator. Then what is the reliability of this evaluation result? Firstly, the sample mean overlap x of QS1 and 2 is 79.42 for this sample of 2 measurements. And the sample standard deviation S for this sample of 2 value is 3.6345. For most fields, the confidence level should be at least 80%. The critical number T for that level and the 2 measurements is 3.078, shown in our figure 1 and 2. Therefore, the margin of error for this measurement is 7.91. This means the confidence interval for these 2 measurements is 7.91 times 2, that is 15.8. This indicates that with an 80% degree of confidence, the true quality score lies on this interval, 79.42 minus 7.91 to plus 7.91. As we can see, given the second measurement, we can significantly improve the confidence interval as compared to the single measurement. The two different judgments that we obtained reduced variance from 25% of the single measurement to 9.96%, that is more than 2 times narrower with an 80% confidence setting. Ideally, we need a third measurement or even more observations to further improve this interval. However, in a production setting, the additional data points are rarely obtained by repeated evaluations due to the cost and time concerns. We already have reliable information for this translation quality evaluation purpose. This is a borderline fail because the sample mean is lower than the threshold, and therefore more than half of the possible values are below the pass threshold. In conclusion, we first studied the typical production setting of gold standard human quality measurement. Translation quality evaluation is performed by one experienced and trained linguist. Then we illustrated the results with a case of student t-distribution analysis of 2 measurements made by 2 different reviewers. A single measurement has very low reliability and indicative value only. The confidence interval of one measurement is as wide as 25%. However, a second measurement can narrow down confidence interval and render it 2 times smaller. Yet, we can say that the middle of the confidence interval lies halfway between the earlier average result and the lower recent measurement. A good sum of rule is that if the single measurement deviates from the average, the true value sits in all possibility halfway between the average and the new measurement. Consequently, the recommendation is please do not overreact on an unusually low new single score. Take a middle ground between the older average and the new score and think about it as the most probable result. Some perspectives from our work. Proper methods of data analysis are required to analyze quality evaluation data sets, such as removal of outliers, which are caused by irrelevant causes. Evaluations made on very small or very large samples. Evaluations that are incorrect due to the improper application of metrics such as counting repeated errors. Evaluations made by reviewers who are not trained, subjective, or had in mind different customer requirements. We thank the WHEEL project for sharing their real translation quality evaluation examples with us to deploy the discussed methods. We thank Dr. Leonore at Purdue University Statistics Department and Professor James of Mathematics at Richard Community College for their open source lectures we used. We are also grateful to the anonymous reviewers for their valuable comments on our work. Thank you. Here are selected references and the link to download our paper. One of the references of Han and Gladkov 2022 is our tutorial given to our REG conference on meta-evaluation of translation evaluation methods, a systematic up-to-date overview. Welcome to have a read. We hope you enjoy Varna and have a good time in RA NLP 2023.